Good morning, honors chemistry students. Today we'd like to look at or examine the hydroxide ion, which is a companion polyatomic ion to the previous video of the hydronium ion. As always, it's important for beginning chemistry students to spend time learning the symbols and charges of the polyatomic ions, and the hydroxide anion has a symbol and charge of OH-1. The second column on your molecular geometry lab involves providing an illustration of the polyatomic ion or molecule once you've completed the modeling exercise that follows this molecular geometry lab. However, for now, we're going to table that and move on to the AELD. In a way, the central atom in hydroxide is the oxygen atom. So we're going to go ahead and ink in the oxygen atom according to Bohr's theory, using this box to represent a nucleus with 8 protons and 8 neutrons, and also recognizing that the number of protons should equal the number of electrons. So in terms of electrons, the first energy level is visualized as holding 2 electrons. And because oxygen's a member of group 6, we say that it has 6 valence electrons that need to be represented, 2 in the S, 1 in each of the P's. And then we're going to go ahead and pair that one up right there. So that's our central oxygen atom. The remainder here, notice that we have to simply represent bonding of 1 hydrogen atom here with its 1 proton and 0 neutrons. So there's another covalent bond. And then one wonders and observes that oxygen's not yet in the octet state, correct? Because it has 2, 4, 6, 7 valence electrons, and it actually needs to possess 8. But then we need to be mindful of that this valence electron that I'm diagramming in red was the valence electron that was left behind by the hydrogen atom that was picked off by another water molecule. And so therefore, now we have a system in which we've got an excess of 1 electron. So therefore, we have 1 more electron than proton. So we're going to bracket this polyatomic ion with a charge of -1. And that's pretty straightforward because you've got 8 protons here for oxygen, 1 for hydrogen, 8 and 1 is 9. And in this system, oxygen has 8 electrons, 2, 4, 6, 8, and hydrogen has 1. So that gives us a total of 8 and 1 is 9. And then by having an extra electron here, that gives us 9 protons. One might say it has 9 protons and 10 electrons. So the difference is a charge of -1. So that's where the charge comes from. It comes from the extra electron that was picked off by the water molecule to form the hydronium ion. The next diagram that we need to represent is the orbital notation. And this, you just need to kind of thoughtfully consider this and try not to panic with what's going on here. Because in orbital notation, you have an oxygen atom which has an S and 3 P's. Its valence shell is on the 2nd energy level, so it's got 2 valence electrons in the S, 1 in each of these P's, and then 1 that is in this P. That's a total of 6 valence electrons. And it's clear that we can show a shared electron pair here from another hydrogen atom. And so you have a P overlapping with an S, and you can show that covalent bond right there. So the question becomes, where does the extra electron go? So we take our handy dandy red marker and come in here and mark in the electron that was remaining from the hydrogen atom that was picked off by the water molecule, and then this creates an overall charge of -1. So once we do the orbital notation diagram, we do the electron dot diagram, and we're going to keep on keeping on with that theme because we've got oxygen with its 6 valence electrons, correct? And we've got a hydrogen that comes in here in bonds with its valence electron. And thus we have one more electron that we need to note, and we're going to, in this case, use a box to represent the valence electron that was left behind by the hydrogen atom. And so we're going to give that an overall charge of -1. So that's pretty straightforward. And then we're going to go on and move on to the structural formula. Which is going to look something like this, in that we're going to have an oxygen bonded to a hydrogen. And in the structural formula, we don't represent lone pairs, so we're simply going to have to bracket this with a charge of -1, okay? And from there, we need to represent the electrons in the system. So we have electrons in this system. Once again, there are 10 electrons overall, but oxygen has 6. This hydrogen has 1, that's 7. And 1 valence electron is 8. We have a total of 8 valence electrons in the system, and we need to compare that to how many are required to be stable. Perhaps the electron dot is the easiest one to use here. Oxygen needs 8, 2, 4, 6, 8. This hydrogen needs 2, 8 and 2 is 10. So therefore, if you want to predict the number of bonds for hydronium, clearly you look at the difference between 10 and 8 and divide that by 2 electrons per bond. So we have a quotient here of 2/2. The 2 represents the number of electrons involved in a covalent bond divided by 2 electrons per bond. So one would predict that we can form 1 bond, or that this molecular system forms 1 bond. So with that, we're going to move to the Lewis dot structure, or Lewis dot diagram, which looks somewhat similar, or is a hybrid to each of these, the electron dot and the structural formula, in that the Lewis dot uses lines to represent shared pairs, and then we have to complete the lone pairs, and we're going to go ahead and use our red marker again to designate the electron which is left behind from the hydrogen. And we're going to bracket this with a charge of -1. Beautiful. That's looking real good. That's real sweet. The next column, we have to look at bond type to determine whether or not the bond between oxygen and hydrogen is polar, which we pretty already intuitively know that it's going to be polar, because the electronegativity of oxygen is 3.45. The electronegativity of hydrogen is 2.20. That difference is 1.25, which falls within the polar covalent region, because once again, if the electronegativity is between 0.0 and 0.4, we say a bond is nonpolar covalent. If it's between 0.5 and 1.7, we say it's polar covalent, and if it's 1.8 or greater, it's referred to as being ionic. So 1.25 falls pretty much in the middle of that range, so we're going to label this as being a polar covalent bond. However, we're not going to show separation of charge here because of the fact that the polyatomic ion is already charged, so it's going to behave as a charged species. So we're going to just leave the structures as is, and we're going to move on to a prediction of the total pairs of electrons around the central oxygen atom. And it looks like, I guess we could use the Lewis dot. We have one bonded pair between oxygen and hydrogen, and we've got 3 lone pairs, so 1 and 3 is 4. So 4 total pairs predicts a tetrahedral arrangement for oxygen. So we're going to come in and develop the VSEPR structure, and keep in mind that 4 total pairs of electrons create a tetrahedral arrangement to minimize the repulsion between the electron pairs. So therefore, I may adjust this just a little bit. We're going to have a bonded pair here, and we're going to have a lone pair here, and we'll represent the, I tell you what, we'll represent this like so. There's one lone pair, and then we're going to have another lone pair behind the paper, and that's the one that's going to have our extra electron from the hydrogen, and then we're going to have another lone pair up here like so. So in essence, we've got a tetrahedral arrangement here with a bond angle of 109.5 degrees and a tetrahedral arrangement of the electron pairs. And keep in mind that this also gets a charge of -1. So we're going to move on from VSEPR to the companion theory, which is hybridization. And we're going to take a look at hybridization theory. And hybridization theory differs from VSEPR in that VSEPR, or VSEPR theory, valence shell electron pair repulsion theory, really is designed to predict the arrangement of electron pairs around a central atom that is not bonded. But hybridization theory is designed to predict, or developed to predict, the arrangement of electron pairs around a central atom that is bonded. So therefore, 4 total pairs predicts a tetrahedral arrangement of those electron pairs in what we refer to as sp3 hybridization. So we're going to have a tetrahedral arrangement of 4 hybrid orbitals. There's a lone pair there, and we're going to have a bonded pair here, and we're going to have a lone pair here, and we're going to have another lone pair here, with one of the electrons coming from the hydrogen that was picked off by the water molecule, and we're going to have a charge here of -1. The bond angle is predicted to be 109.5 degrees, and we're going to say that this is a tetrahedral arrangement. Okay? And then, we can't forget that the predicted hybridization scheme is sp3. Now, in terms of actual geometry, that all looks somewhat complicated, but the reality of it is we're going to represent this, and I'm going to kind of rotate this 90 degrees so that we have an oxygen bonded to a hydrogen, correct? And we're going to have 3 lone pairs of electrons, one here, and one here, and keeping with the electron that was left behind by the hydrogen that was bonded here. And we're going to bracket this and say this has a charge of -1. And in essence, the actual geometry, because you have 2 atoms, has to be linear, because you can draw a straight line through both atoms. So we're going to say that this is a linear molecule, and the bond angle has to be the bond angle of a straight line, which is 180 degrees. Okay? And moving on from that, we're going to go to bond energy. And these values should be familiar with you now, because they're the same values as we use for water and hydronium. The bond energy here is going to be 464 kilojoules per mole. And the bond length is going to be 96 picometers. And lastly, to determine whether or not this polyatomic ion is polar, well, before we get there, I suppose we should do the AXE system. And in this case, wow, what type of molecule would this be? You have two different atoms, so really it's going to be an AB molecule that is in fact diatomic, right, with a linear arrangement. And in terms of polarity, we're going to go ahead and jump out on a limb and say that this is polar because of the fact that it's charged. So that's hydroxide, the hydroxide ion, and you can see that this takes up a little bit more space. Thus, that's the reason on the back side why we only place 4 molecules: hydronium, hydroxide, then ammonium, which you're going to be responsible for, and ultimately sulfate.